In this lecture, we will continue with atomic structure, periodic table, and chemical bonds. In the last class, what we did was we did Schrödinger's equation. So we know this is Schrödinger's equation, and this is the equation that governs quantum mechanics. This is the Schrödinger's equation. Okay, Schrödinger's equation, and this is the one that governs quantum mechanics. In quantum mechanics, the wave function psi is the most important object because theoretically it contains all the information about the quantum system. And how the wave function changes with time is given by the Schrödinger's equation. How the wave function changes with time, del psi delta is equal to h psi, is the Schrödinger's equation, where h is an operator we discussed and it's the total energy operator. And in the last class we also discussed the concept of operators. So operators and eigenfunctions. This we discussed last class, and we discussed that observables are given by observables in quantum mechanics. Observables, that is the things that we measure, are given by operators in quantum mechanics. They are represented by operators, and by using the operators we can extract information about that particular observable from the eigenfunction. And we discussed that corresponding to operators we have eigenfunction. So what is eigenfunction? Like we can have momentum operator. So momentum operator is an operator is given by this p hat. So corresponding to that we can have a momentum eigenfunction denoted by psi p. And what is its significance? Measurement, if you do a measurement of the particle in this state psi p, then measurement, so if you do a measurement, then you always get p. Always you will measure that the particle has a momentum p. Similarly, we can have position operator. Position operator will have eigenfunctions psi x. So when I say psi x, that means when I measure a particle, measure the position of the particle in this quantum state, then we always get x. How many times we measure the position of the particle, we will always get x. It does not matter. Every time, so with certainty, with 1 we will always get x. Here with certainty 1 we will always get p. Similarly, we can have total energy operator. Okay, so total energy operator we know is this, and that we will be denoting by psi, say E. That means if a particle is in this state psi E, then what is its significance? So whenever I am measuring the total energy of the particle, I will always get E. There will be with certainty. Means definitely we are going to get only one value, and that is E. And thing is that if it's not an eigenfunction, so like if we take psi, say, and it is psi is not, say psi is not an eigenfunction. Take an example. So psi is not an eigenfunction. Psi is not an eigenfunction of say x operator. Then what does it imply? It implies that measurement of position, so measurement of position x, will lead to different values. So we will not get one particular value x, but we will get various different values of x. Will lead to different values. Will lead to different values of x. Different values of x. So this is the concept of eigenfunction and eigenoperators. Now we are going to study the hydrogen atom quantum mechanically. So what we are going to study is the hydrogen atom quantum mechanically. So hydrogen atom. So hydrogen atom we are going to study, and the hydrogen atom, so we have one nucleus which is a proton, and so this is plus, and here we have a electron which is minus. Remember, I am not doing orbits, circular orbits, because in quantum mechanics there are no circular orbits like that. So in quantum mechanics, so this is my hydrogen atom, so this is a proton. Okay, so this is electron. So here we have an electron. So this is an electron. Okay, and this is the proton. This is the proton. So proton is considered fixed. So we will consider the proton fixed. Proton is in the nucleus. So proton is fixed. So what we are studying basically is the motion of the electron about this proton. So that is my hydrogen atom. So the state of this electron, quantum mechanical state, the quantum mechanical state state is given by psi. It's a wave function. So psi can be a function of, so this is a three-dimensional problem, x, y or z. It can be like that. So the quantum mechanical state is given by psi x, y, z, and we know that what is psi? Psi is the wave function, and what is its significance? So psi star, that is psi multiplied by its complex conjugate. So psi can be a complex number. So this can be a complex number. So this can be a complex number. So when I multiply it by its complex conjugate, and then dx, dy, dz, what does it imply? It implies this is the probability. So this is the probability of finding, this is the probability of finding the electron. This is the probability of finding the electron between, this is the probability of finding the electron between x and x plus dx dx is a very small quantity, maybe tending to 0, x and x plus dx, then y and y plus dy, comma, and z and z plus dz. So this gives me the probability psi star dx dy dz, where psi can be a function of x, y, z. So this is a three-dimensional problem. The hydrogen atom is the probability of finding the electron between x and x plus dx, y and y plus dy, and z plus z plus d. So this is like a small volume in the. So this is what is. So this is this dx dy dz is like a dx dy dz is like a small volume in space, right? This is like a small volume. This is like a small volume in space, and this gives me the probability of finding the electron in this small volume, particular volume, which is centered about x, y, and z. Okay. So let's go to the problem. So now this is, so the quantum states of, so these quantum states are called electronic states because these are the states of the electron. So for hydrogen atom, now we have to solve this Schrodinger's equation, which we have done. So we will not solve, we will not show the solution. So using this, so solving the Schrodinger's equation for hydrogen atom, what we get is this. The nature of the wave function is like this. Okay. So this is the wave function. So the wave function actually is a function of, you can say it's a function of x, y, and z, and it depends on certain parameters which are called n, l, and m. Okay. So this is my wave function which we get on solving the Schrodinger's equation, and the wave function depends on certain, these are called the quantum numbers. So these n, l, and m are quantum numbers. Okay, are quantum numbers. Okay, these are the quantum numbers. And what is important here is, so this is in this state, in the state psi n, l, m. Okay, these are quantum numbers. So the energy, so energy is certain, like this, if the electron has this wave function, then its energy, angular momentum, okay, we call orbital angular momentum. Okay, this angular momentum is due to the motion of the electron about the proton. So this orbital angular momentum, orbital angular momentum, orbital angular momentum, and magnetic quantum, and the component of angular momentum, and the component of angular momentum along z along Z have definite values. Have definite values. Sorry, have definite values. So yeah, so if we this wave function in this, when the electron is having this wave function, this is energy is definite, its angular momentum or orbital angular momentum is definite, okay, and the component of the angular momentum along z axis has also a definite value. So all these three things have definite values if the wave function is given by this. So this is like this. So this is my z axis, this is my x, and this is my y. So what we are saying is that, so the electron, so the proton is somewhere here, proton is here, so the electron is here, so it is moving around in this three-dimensional space. So this electron has a definite energy E, and it has a definite angular momentum L, and it will have a definite component of angular momentum about the z-axis. So this is my z-axis. So along the z-axis, it will have a definite component. So these three values have definite values. These three observables. So these are all observables, right? These are all observables. This we can observe in an experiment. So these are observables. These are all have definite values. So how does it, so what is N, what is L, and what is M? That is what we are going to see now. N, L, and M. N is the principal quantum number. Okay, N is the principal quantum number. L is called the orbital quantum number, and M is the magnetic quantum number. Okay. And in general, the energy E, the total energy of the electron, is a function of N, L, and M. It's a function of N, L, and M. So here, the principal quantum number can take only integer values. So N can have the values 1, 2, 3, and 4. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it can carry on like this till infinity. So this is the principal quantum number. The orbital quantum number is dependent on the principal quantum number. How? The orbital quantum number L can have values only from 0 to n minus 1. So n is given here. We'll give you an example. So if you are given n, then corresponding to n, the orbital quantum number, or that is that number that defines the total orbital angular momentum, can have values from 0 to n minus 1. And the magnetic quantum number again is dependent on L. So if L is given, the magnetic quantum number or the Z component of the angular momentum can have values ranging from minus L to plus L. With the means minus L to plus L with a difference of 1. So we will see what it means in steps of 1. So minus L, then it becomes minus L minus 1, then it becomes minus L minus 2, like that it becomes 0, and then it will increase in steps of 1 till it reaches plus L. Like this example. So another thing is L is equal to 0. If L is equal to 0, that that quantum state is known as the s orbital. If L is equal to 1, that quantum state is called p orbital. If L is equal to 2, that quantum state is called the d orbital. Okay, so that quantum state is given by d orbital, and L is equal to 1 is the p orbital and L is equal to 0 is the s orbital. So let us see, let us find out what it means this. Suppose n is equal to 1. If n is equal to 1, then what are the possible values of L? 0 to n minus 1. Now n is 1 here, so here your L can have only one value, and that is 0. And what is the value of m? M can take the value minus L to plus L. So if L is only 0, that means m has only one value, that is 0. Okay. So this is one quantum state. Now if n is equal to 2, then what are the possible values of L? L can be 0 or L can be, so 0 and 2 minus 1 is 1. So when n is equal to 2, L can be 0, or when n is equal to 2, L can be 1. Okay, and when L is equal to 0, so what are the possible values of m? That we know already. So possible values of m here, only one value, that is 0. But if L is equal to 1, then what are the possible values of m? This we know from here. So minus L to plus L, that is, it will be minus 1, then 0, and then plus 1. So corresponding to n is equal to 2, there are these two quantum states. And you can see L is equal to 0 is S. Here also this is S orbital. And this is L is equal to 1. L is equal to 1 is p orbital. Okay. And similarly n is equal to 3. So when n is equal to 3, what are the possible values of L? So L can range from 0 to n is equal to 3. 3 minus 1 is 2. So n is equal to 3, so L can take the value 0, or it can take the value 1, it can take the value 1, or it can take the value 2. That's it. And corresponding to L is equal to 0, what is the possible value of m? There is only one, that is 0. For L is equal to 1, possible values of m we have already done here. Minus 1, 0, plus 1. And here for L is equal to 2, what are the possible values of m? You can see m it ranges from minus L to plus L, that is minus 2 to plus 2. So here it will start with minus 2, then increase minus 1, then it becomes 0, and then it becomes plus 1, and then it ends with plus 2. That's it. So these are the three states. These are corresponding to, so these are the states corresponding to n is equal to 3. These are the states corresponding to n is equal to 2, and this is the state corresponding to n is equal to 1. right? So for n is equal to 2, how many states are there? So this is one state, this is one, and here we have 1, 2, 3, right? So 3 plus 1, so there are 4 quantum states. For n is equal to 2, there are 4 quantum states. 4 quantum states. Is it not? For here how many quantum states are there? Only one. So here we have only one quantum state. One quantum state. And what about here? How many quantum states we have? This is 1. So here we have n is equal to 3, l is equal to 1. We have 3. 3 plus 1, 4. And here you have 1, 2, 3, 4, 5. So number of quantum states will be 1 plus 3 plus 5. So is equal to, there are 9 quantum states corresponding to n is equal to 3. So there will be 9 quantum states. Okay, so there are 9 quantum states. So this is how it goes. And you can see, so this is like L is equal to 0 is S, P is equal to, L is equal to 1 is P, and here, so this is, and L is equal to 2, this is SPD. So like that it goes. So this is S, this is P, this is D. So what are the electronic states? How do I define the electronic states? So the electronic states, say hydrogen atom, so what is 1s? What is 1s? This is 1s. This is 1s. So let us change the color here. So this is 1s. N is equal to 1, L is equal to 0, M is equal to 0. This is 1s. So this is 1s. And then we have N is equal to 2, L is equal to 0, and L is equal to 1. Right? So L is equal to 0 is S, and L is equal to 1 is P. For now we are ignoring these states. Okay, so this is 2s and this is 2p. This is 1s. So we have 2s and 2p. So we have 2s and 2p. Okay, so there is multiplicity here. We know that. Here we have actually there are 3 states, and we'll come to that later. And here n is equal to 3. L is equal to 0 is S. So 3S, N is equal to 3, L is equal to 1, that is P, 3P, and N is equal to 3, L is equal to 2, L is equal to is D. So we write 3S, 3P, 3D. So that is how we label the, so we are, what we are doing, labeling the states. We are labeling the states. Labeling the states. The quantum states. So if you consider the energy, so this is the energy diagram. So all these states have definite energy. Right? So these states 1s, 2s, 2p, 3s, 3p, 3d all have definite energies, because we told you that I told you in the beginning that this energy is here, energy is definite. When we say that the electron is in this quantum state, it has a definite energy. So we have definite energy here. So this is the energy scale. So energy increases in this direction. Energy is increasing this direction. So the lowest energy is 1s. So 1s, the electron in the 1s state is having the lowest energy. Then we have 2s. So next highest state is 2s. After that we have 2p, because you can see 1s, 2s. I had already told you that there will be 3 2p states. So this is 1, 2, 3, and all have the same energy. Then we have 3s, right? 3s, there is only one state, and then again p, we have 3p states that I had already mentioned. Next will be this, and then 3p, and then we have 3d. So d will have 5 states. So 1, 2, 3. So we have 5 3d states, and so all these states have the same energy. But then you have 4s state. The 4s state and the 3d state, they are almost equal. The energy, so this energy, so this is almost 4s and 3d are same, isn't it? 4s and 3d have the same energy. 4s and 3d have the same energy. Fours and 3d have the same energy. After that 4s we will have 4p. So we have p means there will be 3 states. So 1, 2 and so 3 4p states. So the energy of these states will be higher than 4s. Then we have 4d. So for 4d we have 5 states. 1, 2, 3. D means 5 states. 1, 2, 3, 4, 5. And then we will have 5s. Again 5s and 4d have the same energy. So 5s and 4d have the same energy. Have the same energy. Five S and 4d have the same energy. So this is the energy graph. So that is how it works. So lowest energy is 1s, and then 2s, then 2p, then 3s, then 3p, then 3d and 4s have the same energy. Then comes 4p, then 4d and 5s have the same energy, so on and so forth. So now we are discussing multi-electron atom, but the same picture, this picture holds for so we are talking about a hydrogen atom, but this one electron states, this picture of one electron states. So the picture, so this is the picture of one electron states. So each state means each state can accommodate one electron. So that's why this picture of one electron states, we'll come to that later. So this big picture of one electron states holds for multi-electron or multi-electron atoms, holds for multi-electron atoms. We'll see what it means. And so when we are talking of multi-electron atom, there is a principle that we have to follow, that is called the Aufbau principle. So let us just go through what the Aufbau principle is. The Aufbau principle dictates the manner in which electrons are filled in the atomic orbitals of an atom in its ground state. Ground state means state of lowest energy. So ground state means state of lowest energy. State of lowest energy. It states that the electrons are filled into atomic orbitals in the increasing order of orbital energy level. According to Aufbau principle, the available atomic orbitals with the lowest energy levels are occupied before those with higher energy levels. So this is the Aufbau principle. So we'll stop here, and in the next class we will discuss what is Aufbau's principle through examples. So we'll stop now, and thank you.